Good evening, everyone. Today, we are excited to present our project titled Deep Learning Based Anomaly Detection and Classification in Surveillance Videos. This project was developed under the guidance of Professor Vaishali, and we are the members Rohan Gunge, Ashish Varghese, Vanessa Nadar, and Neha Nair from Department of IT and Don Bosco Institute of Technology. In today's world, ensuring security in large spaces like campuses and public areas is increasingly challenging. Traditional surveillance systems rely heavily on manual monitoring, where security personnel watch video feeds to detect suspicious activities. However, this limitations. Operators can get tired, distracted, or overwhelmed, especially when monitoring multiple cameras. As a result, critical incidents such as fight, assault, or medical emergencies may go unnoticed or be detected too late for effective intervention. To challenges, researchers have turned to AI and computer vision to automate surveillance. These systems analyze video feeds to identify unusual or suspicious activities. However, existing solutions still struggle with issues like high false alarm rate, poor adaptability, and limited accuracy in real world environment. This brings us to the motivation behind our project. There is a need for an intelligent, automated surveillance system to enhance public security by accurately detecting and classifying anomalies like assault, fight, and medical emergency, enabling timely intervention and ensuring a safer environment for people in controlled spaces guarded by security cameras.
Now, let's look at some key findings from the literature review we carried out to develop a robust anomaly detection and classification system. We explored research in machine learning and deep learning for video surveillance, including journal articles and systematic reviews covering anomaly detection techniques, classification methods, and performance metrics. A systematic review in IEEE Access analyzed 29 machine learning models for anomaly detection, highlighting the growing use of unsupervised learning. However, it didn't address computational efficiency or dataset diversity, limiting its real-world application. A paper in IEEE Transactions on emerging topics in computational intelligence introduced a skeleton-based detection method to enhance privacy by avoiding appearance-based analysis. While this improved privacy, the study lagged concrete accuracy benchmarks and struggled with generalization. An article in IEEE Signal Processing magazine proposed a statistical activity analysis method that worked well in cluttered environments without object tracking. However, it couldn't classify detected anomalies, which is crucial for an effective security response. A study in image and vision computing introduced IVADC FDRL, combining faster RCNN for object detection and deep reinforcement learning for classification, achieving 94.5% accuracy on the UCSD dataset. However, its high computational cost made real-time deployment difficult. Another comprehensive review in image and vision computing categorized deep learning-based models into spatiotemporal and one-class approaches. It highlighted challenges like dataset limitations and ambiguous anomaly definitions, but didn't propose solutions. Lastly, an IEEE Access review covered deep learning in video processing, emphasizing improved accuracy with CNNs, ResNets, and LSTMs. However, it didn't address the feasibility of real-world deployment. These gaps highlight the need for an intelligent, efficient, and adaptable system, precisely what our project aims to achieve.
Next, we will explore how a solution addresses these issues and enhances security through advanced AI and deep learning techniques. To address the identified gaps in existing research, our project focuses on developing a machine learning-based anomaly detection and classification system for surveillance videos. The objective is to accurately detect and classify abnormal activities such as fights, assaults, and medical emergencies like collapsing by leveraging both spatial and temporal analysis techniques. The model we designed systematically detects anomalies and classifies them into specific categories rather than treating all anomalies as a single event. This classification is crucial because different types of anomalies require different responses. While many anomaly detection models are computationally intensive, we have optimized our approach to balance accuracy with efficiency, making it feasible for real-world applications. This solution is designed not only for deployment within new surveillance setups, but also for integration into existing security systems. Additionally, Our results provide insights into the performance of different machine learning techniques, enabling further advancements in the field. However, it is important to clarify that our project's primary scope is model building and systematic validation on unseen video samples to evaluate accuracy, generalization, and performance. The trained model is integrated into a Flask-based user interface where users can upload videos for anomaly detection and classification. This UI serves as an interactive platform to visualize the results and validate the model performance in a controlled environment. Now that we have outlined our proposed solution, we will move on to the methodology, where we will discuss the step-by-step process involved in developing the system. Let's first take a look at how a dataset is structured. All data is stored on Google Drive in an hierarchical format, ensuring systematic and efficient access during training. The dataset consists of pre-processed videos, which are already resized and normalized with trained test scripts, and extracted frames stored in directories corresponding to their category: normal, collapse, assault, or fight. Additionally, feature vectors extracted using EfficientNetBio are saved as .mpy files for fast retrieval. Now, let's walk through the model pipeline. The process begins when user uploads a video in .mp4 or .avi format, which is then pre-processed by extracting frames, resizing them, and applying necessary transformations. The processed frames are passed to EfficientNetBio for feature extraction, where each frame is converted into a 1280 dimensional feature vector and normalized using L2 normalization to ensure stable numerical values. These extracted features are then fed into the multi-instance learning model for anomaly detection. Instead of classifying each frame individually, MIL treats an entire video as a bag of frames and predicts whether an anomaly is present. If no anomaly is detected, the video is classified as normal and no further processing is required. However, if an anomaly is detected, the extracted features are passed to the temporal convolutional network (TCN) model for classification. The TCN model consists of multiple layers of 1D convolutions with dilated connections, enabling it to capture long-term dependencies in video sequences. An attention mechanism highlights the most relevant temporal patterns, ensuring the model focuses on critical motion changes. Finally, a softmax layer outputs the probability distribution over possibly anomaly classes, categorizing the event as collapse, assault, or fight.
Initially, we have imported all the necessary libraries and models we required for this project. The notable libraries such as OS, NumPy, and TensorFlow framework, including all the necessary models such as Keras, which include all the optimizers such as Adam models necessary for our project have been imported here. The initial step is extracting frames from the videos. We use OpenCV's video capture to read videos and extract frames at regular intervals. The extract frames for all videos function iterates through the video directories, processing videos in batches to extract a fixed number of frames per video, that is 32 in this case. Frames are resized and padded to maintain aspect ratio and consistent size of 224 into 224 pixels. Next step is of feature extraction. After extracting frames, we use pre-trained EfficientNet B0 model to extract features from each frame. This model is known for its efficiency and accuracy in image classification tasks. The extract and save features in batches function handle this process, loading the model with pre-trained weights from ImageNet. It iterates through frame directories, loading each frame, pre-processing it using pre-processed input, and then using EfficientNet V0 model to predict the features. These features are then saved into batches to disk for later use in training of the classification models. Next step is training our anomaly detect classification model. For anomaly classification, we employ a multiple instance learning model. The build MIL model function defines this model, incorporating dropout, L2 regularization, and attention mechanism to enhance the model's performance. Importantly, the model architecture is tuned using Keras tuner with a hyperband search strategy. Hyperparameters like the number of units in the dense layers, dropout rate, and learning rate are optimized to minimize validation loss. The mesh model is then saved for further training and evaluation. The main function orchestrates the entire process. It initializes data generator for training and testing, calculates the class weights to address class imbalance using scikit-learn computes class weight function, perform hyperparameter tuning, trains the mesh model with optimal parameters, and finally evaluates the model's performance. Performance metrics such as classification report, confusion matrix, ROC, AUC, average precision, and precision recall area under the curve are computed and visualized using matplotlib and Seaborn. These metrics provide insights into models' ability to distinguish between normal and anomalous events. Now, we trained another model to classify exactly the type of anomaly that has occurred. After binary classification, we further categorize the anomalous videos into specific types such as fights, assault, and collapse. This is a multi-class classification task. The feature extraction process using efficient net B0 that we did earlier remains the same, but the labels are now assigned to 0 for fight, 1 for assault, and 2 for collapse. We use temporal convolution network (TCN) with attention mechanism for this task. The build TCN with attention model function defines the architecture including temporal blocks, attention blocks, global pooling, and a classification head. The training process uses class weights to handle potential imbalance in database. We monitor training progress and evaluate the model on the test data using metrics such as accuracy, loss, classification report, and a confusion matrix. The confusion matrix provides a detailed breakdown of the model's performance for each anomaly type. Now, let's move on to the results. During training, we sought to identify the best hyperparameter values that minimize the validation loss. The tuner initially reported a validation loss of 1.1654, though iterative exploration, the best validation loss is achieved was 0.82898. This indicates that our model has effectively learned patterns to distinguish between normal and anomalous videos, resulting in lower validation loss. For model evaluation metrics, we employed several metrics to assess model's overall performance. Test loss, a measure of how well the model performs on unseen data. Here, our model obtained a test loss of 0.8875, which is close to the best validation loss achieved during training. This indicates the model generalized well to new unseen videos. Test accuracy represents the percentage of videos correctly classified. We achieved a test accuracy of 0.7333, which approximately indicates that the model correctly identified the category normal or anomalous for approximately 73.33% of the test videos. We'll look the classification report to understand the model's performance across the two classes. Precision, a measure of model's accuracy when it predicts a video to be anomalous or normal. Both classes have the precision of around 0.74. Recall, the measure of model's ability to correctly identify all anomalous/normal videos. Both classes have a recall of around 0.74. F1 score combines precision and recall to provide an overall measure of model's performance for each class. Both classes have an F1 score around 0.74. The confusion matrix provide a more detailed picture of classification results, showing the true positive, true negative, false positive, and false negative counts for each class. We also use ROC, UOC, AUC, and precision recall area under the curve to further evaluate our model. These scores reflect the model's ability to distinguish between two classes with an area under the curve score closer to 1, indicating better performance. Our model has ROC AUC of 0.7417, an average precision of 0.6783, and a precision recall AUC of 0.8064, reflecting a reasonable level of discrimination. We will briefly review the performance of our multi-classification model for anomaly detection in videos. The model achieved a test loss of 2.82 and accuracy of 60%. That means the 60% of videos in the test set were correctly classified. Looking at the classification report, we see the precision, recall, and F1 score for each class, fight, assault, and collapse. For example, the model correctly identified 62% of the actual fight videos at fight precision out of fight videos. It is identified 82% of them recall. The F1 score combines precision and recall, showing the score of 0.71 for fight. The confusion matrix provides the visual representation of model's predictions. Each row represents the true class and each column represents the predicted class. For example, for fight, 22 fight videos were correctly classified as fight. However, the model classified 8 assault videos as fight. Diagonal entries represent the correct classification, while off-diagonal entries indicate the misclassification. Our model demonstrates the promising performance, and these metrics indicate a model that generalizes well, correctly classifies a substantial portion of test videos, and exhibits a good ability to differentiate between normal and anomalous videos and further classify them into individual categories. Now let's take a look at our Flask application. We have trained both the multi-classification model and binary classification model and uploaded it in our local VS Code file in our Flask application. We have created a useful user interface that enables user to upload the surveillance footage. Now, this is the test video that we are going to upload. Once we upload the video, we'll press the upload button. As you can see, the processes that we mentioned of frame extraction and feature extraction are running in the background. once we the entire classification process is done, we can see the result in front of our screen. As you can see, there's a fight occurring in this video. So the anomaly detected was flagged as yes, and it was further classified into a subtype such as fight. Accurate. Now let's test the model again on another unseen video. As you can see in the following video, a person is coming in and collapsing down on the mattress. So the anomaly detected was flagged as yes, and it was further classified into a collapse. This results into show how the model is well trained to distinguish between the type of anomalies. Now let's go and check for another video. As you can see in this video, there is no type of anomaly occurring in the following video. The person is just walking out of the particular complex. So we can see the anomaly detected is no. And as the anomaly is not detected, there is no need to call for the second model for further classification. Thus, this simple UI or the Flask application enables user to test the model and get a grasp of this concept. For the project, we have, as we mentioned in the literature review, we went through a variety of papers. The references are mentioned in the further slides. This is it for the end of the project demonstration. Thank you, everyone.